Welcome to this lecture on the basics of neuroscience. Today, we are going to explore one of the most fascinating topics in biology, how our brain cells, called neurons, communicate with each other. We will uncover the secrets of the resting membrane potential, which acts like a tiny battery, and the action potential, which is the explosive electrical signal that allows you to think, feel, and move. Let us dive in and see how this microscopic electrical system works. To begin our journey, let us imagine a tiny microscopic battery floating inside your brain. Just like the battery in your smartphone stores energy to power the screen, a neuron stores electrical energy to send messages. When a neuron is just sitting there, not sending any signals, we say it is at rest. But this rest is not a lazy state. It is a highly active, tense state of readiness, much like a bowstring pulled back and waiting to be released. To create this tension, the neuron acts like a salty banana. It is full of potassium on the inside and surrounded by salty sodium on the outside. This separation of chemicals creates a tiny electrical charge across the cell membrane. Now that we understand the neuron acts like a battery, let us look at the exact voltage it holds. The resting membrane potential is the electrical difference across the neuronal membrane when the cell is not actively firing. In a typical neuron, this resting voltage is about minus 65 to minus 70 millivolts, meaning the inside is negatively charged compared to the outside. Why is it negative? It is primarily maintained by two things. First, the membrane has selective permeability, which lets positively charged potassium leak out easily, leaving a net negative charge behind. Second, the sodium-potassium pump actively pushes sodium out and pulls potassium in. Without this electrical difference, the neuron would be completely dead and unable to communicate. This delicate balance of ions leads us to an important mathematical tool called the Nernst equation. Conceptually, this formula calculates the exact voltage at which the chemical push of an ion is perfectly balanced by the electrical pull, a state known as the equilibrium potential. Let us break down the symbols. E-ion represents the equilibrium potential for a specific ion, measured in millivolts. The number 61.54 is a constant derived from human body temperature and other physical constants. The terms in the fraction represent the concentration of the ion outside the cell divided by the concentration inside the cell. If the concentration of the ion outside increases, the ratio becomes larger and the equilibrium potential becomes more positive. This equation allows us to predict exactly how the neuron will behave. Before we move on, let us see this formula in action with a concrete example. We want to calculate the equilibrium potential for potassium in a typical mammalian neuron. We are given that the concentration of potassium outside the cell is 5 millimolar, and the inside is 100 millimolar. We need to find the voltage at which potassium is in perfect balance. We start by plugging our outside and inside concentrations into the Nernst equation, giving us 5 divided by 100. This fraction simplifies to 0.05. The base 10 logarithm of 0.05 is approximately negative 1.301. We multiply this by our constant of 61.54. Our final answer is approximately negative 80.06 millivolts. Physically, this means if the membrane were only permeable to potassium, the resting voltage would be exactly negative 80 millivolts. Now that we have calculated the potential, let us look at a visual representation of this resting state. On the screen, you are seeing a cross-section of the neuron's cell membrane. Notice the extracellular fluid at the top, which is packed with sodium ions, and the inside of the cell at the bottom filled with potassium ions and large negative proteins. Look at the sodium-potassium pump embedded in the membrane. It is actively working to maintain this separation. Right next to it, you can see a leak channel where potassium ions are escaping to the outside. Finally, observe the voltmeter on the right, which measures the net result of all this activity, a resting membrane potential of minus 65 millivolts. This diagram perfectly captures the tense, ready state of the neuron. With the resting state fully established, we can now explore what happens when the neuron actually sends a message. If the resting potential is a drawn bowstring, the action potential is the release of the arrow. Imagine you are at a sports stadium and the crowd starts doing the wave. One person stands up, throws their arms in the air, and sits back down, triggering the next person. An action potential works exactly like this stadium wave, but with electrical charges traveling down the length of a nerve fiber. It is a sudden, explosive spike in electricity that travels from one end of the neuron to the other. This is the fundamental unit of communication in the nervous system, allowing your brain to tell your toes to wiggle in a fraction of a second. So, how exactly does this explosive stadium wave begin? This event is triggered when the neuron's resting voltage is pushed past a critical threshold, usually around minus 55 millivolts. Once this specific threshold is crossed, special voltage-gated sodium channels in the membrane suddenly pop open. Because sodium is highly concentrated outside the cell, these positively charged sodium ions violently rush into the cell. This sudden influx of positive charge causes a massive, rapid spike in the membrane voltage, a phase we call depolarization. The inside of the neuron briefly becomes positive relative to the outside. This rapid reversal of the membrane potential is the very heart of the action potential. Immediately after this massive spike, the neuron must reset itself. Shortly after opening, the sodium channels close and voltage-gated potassium channels open up. This lets positively charged potassium rush out of the cell, which restores the negative resting state in a phase called repolarization. It is important to note that this entire process is all or none, meaning it either happens completely or does not happen at all, just like flushing a toilet. Furthermore, action potentials are absolutely critical because they constantly regenerate themselves along the nerve fiber. If you step on a tack, the pain signal must travel all the way to your brain. The action potential ensures the message arrives with the exact same strength it had when it started. To understand the sheer power behind this rush of ions, we use a modified version of Ohm's law for membranes. Conceptually, this formula tells us how strongly ions want to cross the membrane during an action potential. Let us look at the symbols. I-ion represents the electrical current of the ion flowing across the membrane, measured in amperes. The symbol G-ion stands for the conductance, which simply means how many channels are open for that ion to pass through. Finally, the part in the parentheses, Vm minus E-ion, is the driving force. Vm is the actual membrane voltage, and E-ion is the equilibrium potential. If the driving force is large, ions will rush across the membrane very quickly. If the membrane voltage equals the equilibrium potential, the driving force becomes zero and no net current will flow. Let us apply this driving force concept with a practical example. We want to calculate the driving force for sodium when a neuron is at its resting membrane potential. We are given that the resting membrane potential, Vm, is minus 65 millivolts, and the equilibrium potential for sodium, ENA, is positive 62 millivolts. We need to find the force pushing sodium into or out of the cell. We use the driving force portion of our formula, which is Vm minus ENA. We substitute our values, giving us minus 65 minus 62. Mathematically, this combines to create a much larger negative number. Our final answer is negative 127 millivolts. Physically, this large negative value indicates a massive electrical and chemical pressure pushing sodium ions into the cell, perfectly explaining why sodium violently rushes in when channels open. Now that we have calculated the forces involved, let us look at the classic action potential voltage graph. On the screen, you see a graph with time on the horizontal axis and membrane potential on the vertical axis. Follow the blue line starting at the resting potential of minus 65 millivolts. Notice the dashed line at minus 55 millivolts. This is the critical threshold. Once the blue line hits that threshold, you see the massive, steep upward spike reaching positive 40 millivolts. This is the depolarization phase, driven by sodium rushing in. Then, the curve drops sharply back down during repolarization as potassium rushes out. It even dips slightly below the resting state, a phase called hyperpolarization, before finally settling back to rest. This graph beautifully summarizes the entire electrical firing cycle. We have covered a lot of ground today, so let us summarize the key takeaways. First, remember that the resting membrane potential acts like a charged battery, storing potential energy through the careful balance of sodium and potassium ions. Second, we learned that the Nernst equation allows us to calculate the exact equilibrium voltage for any of these ions. Finally, we saw that action potentials are rapid, all-or-none electrical spikes driven by massive driving forces when ion channels open. These elegant mechanisms ensure that signals from your brain reach your body instantly and without losing any strength. You now have a solid understanding of the fundamental electrical signals of the nervous system. Great job!